In this online video, we're going to talk about synchronization procedures in Java. And the best place to look for notes on this lecture is at the Java concurrency tutorial, which you can find by following the web link on my notes, lecture notes website for the course. Because you are seeing threads in at least two other courses, 360 on systems programming and 361 operating systems, we're not going to spend a lot of time talking about the reasons why we need to have synchronization. We'll review them briefly, but what we're primarily concerned with in this course is the language level mechanisms for providing synchronization, as opposed to the library mechanisms that you have for synchronization in C and C++. First, let's review the need for synchronization. There's two reasons why we need to synchronize or coordinate the actions of a group of threads. The first is something that the Java tutorial calls thread interference, but is more generally known as a race condition. You have some kind of contention for shared resources, such as a counter, and you need to make sure that the threads access that counter in an orderly fashion. Now, as the book points out, not all race conditions are bad race conditions. For example, we might have a set of threads that are accessing a task queue, and they're dequeuing tasks and executing them one at a time. So, well, each thread is executing a task one at a time, but you have multiple threads, so multiple tasks may be executing in parallel. In this case, we really don't care which thread is accessing the task queue at any time, because we don't care which thread executes a task. So that's not a bad race condition. We are content to live with that type of race condition. So we're only concerned with trying to eliminate bad race conditions. The second type of issue that we're concerned with is something called memory inconsistency. The Scott textbook calls it memory coherence. And that occurs when we have what is called a happens before relationship, where thread A relies on thread B to do a write before it does a read. So if B somehow were to do the write and A were not to see it, that would be a memory inconsistency. And that can happen somewhat easily in threads. One reason is because in Java, the threads maintain their own local copies of variables, typically in registers, and they don't necessarily force those writes back out immediately. So if A is waiting on B to write some variable X, and B writes to that variable X, A may never see the write because A is keeping its own local copy of X in a register, and similarly B is keeping its copy of X in a register, and therefore A may not see B's write. So we have to have some mechanism by which we can force the write from B to memory and also force A to read that write from memory rather than from its register. We're going to first talk about synchronization techniques for race conditions, and then we'll talk about synchronization techniques for memory consistency. There's three techniques that Java provides for avoiding race conditions. The first is synchronized methods, which is akin to monitors. You may have read about them in the book. You've almost certainly heard about them if you've taken the operating systems course. There are synchronized statements, which the book calls conditional critical regions. And there are something called atomic variables, which provide atomic updates for certain types of atomic updates for variables. What Java does not provide, because it's lower level, is the so-called semaphore technique, which is typically what you would implement if you were implementing it through a library. And the difficulty you may have seen if you've tried to implement a pthreads version of the semaphore is that the code tends to get scattered throughout the code rather than being centralized in one location. The synchronized methods and statements techniques that you find in Java centralize all the code in one place, so it's easy to see what's going on. Let's start with synchronized methods. And what we have here is a synchronized counter. So you can see that we can add the synchronized keyword before a method. And here we have a synchronized method for incrementing a counter variable C, for decrementing it, and for returning its value. The reason we need to synchronize is that when we increment or decrement a value, that's not an atomic operation. It actually consists of 3 operations. First, we retrieve the current value of C. Second, we increment that value by 1. And finally, we store that incremented value back into C. So the issue, if this class is not, its methods are not synchronized, is let's say that we have a thread A that tries to call the increment method to increment C from 0 to 1, and a separate thread B that tries to call the decrement method, which would decrement C from 0 to -1. And it's possible, because the increment and decrement operations are not atomic, that we could get an interleaving. So here's one possible bad interleaving. Thread A retrieves C. It gets preempted, and thread B starts executing, it retrieves C. So they both get a value of 0. Thread A now comes back and gets the CPU, increments its value to 1, but it's still in a register in A, and it turns the CPU over to B, which decrements its value, and the result is now -1, which is also holding in a register. Now thread A gets the CPU back, flushes its register, and C now contains 1. Now B gets the CPU, flushes its register, and C is now set to -1. You can see this is not the right outcome. The right outcome is that C would be 0. Either B would first do a decrement, setting it to -1, and then A would increment it back to 0, or A would get it first, increment it to 1, and then B would decrement it back to 0. And I understand that this fine-grained interleaving is perhaps not likely, but it shows what could happen, and it is a possible bad interleaving. It could happen in a CPU, especially if there was some other interference going on. What the synchronized method does is that it says that anything in the synchronized method has to be performed atomically. So no other procedure can call increment while the procedure is executing. However, it's an even stronger statement than that, which is that no other synchronized method in synchronized counter can execute either, which means decrement may not execute while the increment method is executing. And that's exactly what a monitor does. Only one of its operations may be executing at any point in time. So if A is able to get its increment first, B will be shut out until A has finished incrementing the counter. And then when the increment exits, what happens is that all the registers are flush. So all values that were computed during the increment method are flushed back to memory. Therefore, when the decrement executes, those updates will be visible. So synchronized methods also introduces a happens before relationship, because a synchronized method that executes will flush all of its changes to memory before the next synchronized method in that class is allowed to execute. Sometimes synchronized methods are too chunky, especially if a synchronized method has a very expensive operation. It could cause other threads to starve. They are simply waiting, and there's no reason for them to wait if the critical part or critical section of the synchronized method does not include the very expensive operation. So here we have an example where we want to have an add name function that is going to set the last name to be a name, increment the name count, and then it's going to add the name to a name list. And it turns out that we don't care in what order names get added to the name list. We only want to make sure that the counter gets incremented properly and that the last name variable gets set to whatever the name is, and that there not be a conflict. Furthermore, the add method may be a little more time consuming. Therefore, we don't want it in the critical. It's not part of the critical section, and we don't want it in the critical section. We want other pieces of code to have access to add name once we're out of the critical section. The way we can do that is adding synchronized statements. It's a synchronized block, and you acquire a lock. Every object has a lock, a single lock. And in this, you acquire it with a synchronized statement by giving a reference to the object. So in this case, we acquire the lock on the current object. We're able to set its instance variable last name to name, its name count we increment. We then release the lock as we exit the synchronized statement, as well as flushing the changes. And now other threads are going to be able to call add name even though we're still in add name and calling the add method to add the name to name list. The obtaining the lock using the synchronized statement prevents other object or other threads from obtaining this lock until the synchronized block exits. The synchronized methods do the same thing. They implicitly obtain the lock on the object, whereas the synchronized statement explicitly obtains the lock on the object. And these locks are reentrant. If add name called another method in this object, since we have the lock, we would be able to execute a synchronized statement in another method because we already have the lock. So we wouldn't block in another method when we tried to execute the synchronized statement and obtain the lock for this object because this thread already owns that lock. So here's an example of using multiple locks and being able to have different synchronized sections. So we're going to assume that we have an election class that is counting ballots for two candidates. And we want to be able to access the two counters separately. There's no reason to synchronize the two counters because if thread A wants to update the count for candidate 1 and thread B wants to update the count for candidate 2, there's no race condition. So synchronizing the methods would be too restrictive. Instead, we want to use a synchronized statement. However, if we had to use here synchronize this and synchronize this, we would still run into the problem that threads A and B have to compete for the election object's lock. What we can do instead is create two new generic methods, which we've done up here, calling them lock1 and lock2. Since each object has a lock, creating a new instance of an object gives us a lock. Now it's a bit heavier weight perhaps than we would like, and Java version 5 introduced a specific locking class, which we will look at in another lecture. But this is one way to obtain a lock. And now, candidate 1, we can have them synchronize on lock 1. Candidate 2 can synchronize on lock 2, and therefore threads A and B can separately and simultaneously update their candidates' counts. Just a quick review of synchronized methods and statements. They force all the thread's variables to be updated from main memory on method entry. So you don't operate off the register values that the thread is kept. Instead, any instance variables it may have had, those are read from memory. Second, on memory exit, all the changes to the thread's variables are flushed to memory. So anything being kept in a register or a cache is flushed back out to memory. Thus, the next method that calls a method of this object will be able to obtain the updated values of the variables. And finally, both synchronized methods and statements obtain and release a lock on an object. Synchronized methods do it implicitly. They obtain the lock on the object that the method is a part of. Synchronized statements do it explicitly and are not required to obtain a lock on the object that the synchronized statement is part of. They can obtain a lock on another object, as was done here, where we declared two separate lock variables, 1 and 2. The third way that we can synchronize variables in Java is using atomic variables. And this works only for fine-grained synchronization. So you'd use methods and synchronized statements for more coarse-grained critical sections. Atomic variables refer to updates to single variables. And in fact, there are a few guaranteed atomic accesses. So one of them, any 32-bit entity or less, is guaranteed to have atomic reads and writes in it in Java. So anything but a double or a long is guaranteed to have an atomic read and write. Furthermore, and we'll discuss these variables in a moment, volatile variables. If you declare a variable as volatile, it's guaranteed, no matter how long it is, that a read or write is atomic, meaning that it's not just read into a register, but in fact, when you try to write it, the value is updated and written back out to memory. However, there are times, like with counters, where you need to be able to do more than simply have a read or write. You may want to increment a value. And for those, Java has a package, the java.util.concurrent.atomic package, that defines a number of different atomic variables. They're essentially wrappers for the primitive types, like integers, doubles, booleans. And these classes provide a number of update operations that are guaranteed to be performed atomically. So here we have an example of a counter which is doing exactly what we were doing a few minutes ago with this synchronized counter, but now we're just using an atomic variable called an integer. So we're declaring an atomic integer whose value is initially 0. Our increment now simply calls c.increment and get, and what that does is increment the value of c and returns its value. We don't care about the return value, so we simply call the increment and get method. Similarly with decrement, we simply call decrement and get, and it atomically decrements it and returns the value. And then c.get will retrieve whatever the current value is. So these two operations, increment and get and decrement and get, do the three operations described earlier of retrieving the value from memory into a register, incrementing the register, or decrementing it, and then flushing the register to memory. So if we have a simple variable like this, we may want to consider the atomic variables. And if you just go and look at the API for any of these variables, then you can see that they have a number of operations, and it's not just increment. You could do an add of some value, not one, but any value. You could do what's called a compare and set, which means that you optimistically update the value and then you put it back in there, and the set is done only if the expected value is the same as the updated value. And where this typically would happen is, let's say we retrieved the value of the variable and that it was 6. We now do some series of operations on it. Not an atomic operation, but perhaps we execute some number of statements, eventually updating the value to 10. We now want to write that value back into memory. And the issue is, let's say that in the meantime, some other thread, thread B, got in there and changed the value to 8. We would then know that if we wrote this value 10 back, we're clobbering what thread B did. And therefore, we would like to not write the value back. We want to repeat the computation, probably now using 8 as our value. So this compare and set, what it does is says only write that value back, in this case the value of 10, if the value is 6. Because then we know that no other thread has made a change, or if the other threads did make a change, that current value 6 corresponds to the value that we had. And we sometimes use this kind of compare and set when we're doing what's called implicit synchronization. We don't care if we have to roll back the operation that we've performed. This is often called transactional computing. So in transactional computing, you talk about some transaction as doing a set of computations and then looking to commit the changes, which is what, in effect, the compare and set operation does. If they can't be committed, then we roll back the operation, or we roll it back and attempt to do the transaction again. So this is called implicit synchronization because we are implicitly synchronizing with other threads that may be changing this value here. So B, another thread, may beat us to it, in which case we'll have to roll back and then repeat the transaction. We will end up having properly synchronized in this case because B will have performed its operations before us. We will have some inefficiency because we had to roll back the operations. However, explicit synchronization also has overhead associated with it in terms of obtaining and releasing locks and having to flush stuff from memory as well as read things from memory. So if we don't expect there to be a great deal of contention for certain resources, we may want to go with implicit synchronization rather than explicit synchronization. And hence, these atomic variables provide a way of supporting that with the compare and set method. And I'll let you look at the other methods as part of it, but these are the primary ones: is add and get, increment and get. So these increment and decrement operations, and then a general setting operation.